Tejinder Pal Singh is a distinguished theoretical physicist, formerly with the Tata Institute of Fundamental Research, renowned for his work on quantum foundations, gravity, and cosmology. He earned his PhD from TIFR in 1989 and subsequently held postdoctoral and visiting positions, including at the Inter-University Center for Astronomy and Astrophysics. For a career spanning more than 3 decades, he progressed through various academic roles at TIFR, contributing significantly to research and mentoring in high energy physics and quantum theory. His research focuses on developing deeper connections between quantum mechanics and gravity, with notable works on spontaneous wave function collapse models, quantum to classical transitions, quantum interference in time, and generalized theories of gravity. Professor Singh has also contributed to studies of cosmological constant problems, dark energy, gravitational collapse, and torsion-based gravity theories. Widely respected for his conceptual clarity and theoretical insight, he continues to be active in advancing foundational questions in modern physics. And now, without further delay, it is my great pleasure to invite Professor Singh to deliver his lecture. Sir, please.
Thank you for your very, very kind introduction. Yeah, I would also like to thank Bhaktivedanta Institute for giving me the opportunity to present these ideas here. It is my second interaction with the Institute. I was there physically in person last year in Kolkata for the quantum mechanics, foundations of quantum mechanics meeting. It was a pleasure. It's a pleasure to be back. I also want to thank our previous speaker, Professor Livio, for giving such a beautiful lecture and setting a very nice flavor with his excellent and enjoyable presentation. So I have to try to meet those high standards. And also there is now a change of flavor, yeah. We are going from understanding life in the universe to the more physics questions. So my point in this talk is that if we want to understand how the universe began and how it will end, we must first have in hand those laws of physics which are necessary for that work. So, right. So, what is the connection between cosmology and physics? Our understanding of the universe is limited by our understanding of the laws of physics. In particular, the laws of quantum theory, of gravitation, and of particle physics, basically all of fundamental physics. If we don't understand those laws well enough, we cannot successfully and reliably understand the beginning of the universe. And there is currently a limitation to our theoretical understanding. Like we don't have a theory of quantum gravity. It's not that, it doesn't mean we will never have, but right now we don't have. So the highest energy scale that we can understand theoretically today is about TeV, which is around 1000 GeV, 10 to the 12 electron volts. In the early universe, this is the electroweak symmetry breaking scale. We don't know how the universe began. If it began with the Big Bang, then the highest energy scale, assuming that it is finite, would be the Planck energy scale, which is 10 to the 19 GeV. And what we have understood so far is a much lower energy scale, about 1000 GeV. So we understand physical laws up to about 1000 GeV, and we have to go all the way up to 10 to the 19 GeV. So at this energy scale, at the TeV energy scale, the universe was about 10 to the power minus 12 seconds old. So assuming it began with the Big Bang, and we know it is 13.8 billion years old today in the standard cosmological model. We understand physics all the way back to 10 to the minus 12 seconds, which is very impressive. But we need to understand these before 10 to the minus 12 seconds also, because Planck time, the smallest fundamental unit of time, Planck time, is 10 to the minus 43 seconds. So although 10 to the minus 12 is small, 10 to the minus 43 is much, much smaller. It is about 31 orders of magnitude less. So that whole 31 orders of magnitude, we don't know what happened there. We can only make ideas. So what was the universe like before 10 to the minus 12 second? We do not know. So what is holding us back? Various reasons. Why don't we know before this time? Well, particle accelerators like the LHC, the Large Hadron Collider, have not yet crossed the TeV scale. People want to make accelerators with, it can probe higher energies, but it is extremely expensive. But it is not just experiment. Theory also is lagging behind. In fact, theory is lagging behind experiment. Why do I say that? Experiment has given us a lot of data. The standard model of particle physics, strong force, weak force, electromagnetism, all have been discovered. Why are there these three forces? Why do they have these particular symmetry groups, SU3, SU2, U1? And most importantly, the experiments and the accelerators have given us dimensionless coupling constants like the fine structure constant or the ratios of masses of elementary particles. We need to explain why these dimensionless constants take these particular values. We cannot say that, oh, we don't know the answer because we don't have an accelerator beyond TeV. Is that the real reason? We don't know. Maybe theory is lagging behind. We do not have a theory of unification of all forces. We do not have a theory of quantum gravity. So, to understand the beginning of the universe, we must first develop quantum gravity and unification. And my thesis is that the reason we are stuck is because there are foundational problems of quantum theory which need to be first solved to make progress towards quantum gravity and unification. So, my work over the last couple of decades has been in this direction to address specific questions in quantum theory. And in the process of solving those questions, I found that we are inevitably led to a theory of quantum gravity and a theory of unification. And that is the story I want to tell you today in brief, and how what that is then telling us about cosmology, or about the universe at large. Right. So there is one particular foundational problem of quantum theory which is central to this whole development. I call that the problem of time in quantum theory. So what is the problem? In quantum theory, evolution is described using a time parameter which is classical. What does this mean? So when you write the Schrodinger equation, IH bar del psi by del t equals h psi, that t that is appeared, that time parameter is not quantum in nature. It is part of a classical space-time. You could say that time is not an operator. Position of a particle is made into an operator, but time is not made into an operator. Time is classical. It's a real number. And that is a problem in the following sense. Why? Classical, so time is part of a classical space-time. Classical space-time is produced by classical macroscopic bodies such as stars and galaxies. So according to Einstein's theory of general relativity, space-time has curvature, and the curvature of space-time is the same thing as gravitation, and this is produced by macroscopic large bodies, stars, galaxies, clusters of galaxies. But it is not just the gravitational field, it's not just the curvature, it is space-time itself, what we call the space-time manifold. X, Y, Z, T are the coordinates of space-time. That is a fabric, that is the underlying arena in which bodies live. I'm saying, okay, I will not go into the details today, that if you want to meaningfully talk of the space-time manifold itself, the fabric of space-time, the points of space-time, then the universe must be dominated by classical macroscopic bodies. This can be made a formal argument. I will not go into it right now. So, what am I saying? Classical space-time and classical macroscopic bodies cannot exist without each other. If the universe is dominated by classical objects, the space-time manifold will be point-like. If the space-time manifold is point-like and if it can be defined as a fabric, it means material bodies must exist. In other words, in my way of looking at it, there is no meaning to an empty space-time. If you think that universe is everywhere flat and there are no bodies in it, I say that that is unphysical. We don't observe such a universe. The only universe we observe has matter and radiation, and it has space-time. I'm saying in order to talk of space-time, you need the universe to be dominated by classical bodies. However, classical macroscopic bodies are a limiting case of quantum systems. So, what is going on? Quantum theory needs the external classical time. That classical time is possible to be produced only if the universe is dominated by macroscopic bodies. However, but these classical bodies are a limiting case of quantum systems. You put a lot of atoms together, that is how you get a planet or a star. So, you see with this logic that quantum theory depends on its own limit. How? Because quantum theory needs classical time. Classical time is possible only if there are macroscopic bodies in the universe, but macroscopic bodies are a limiting case of quantum theory. So quantum theory depends on its own limit in a circular way. By depending on classical time, quantum theory depends on its own limit, which means that the description of quantum theory that we have today can only be approximate. It is not exact. It is extremely successful. It is matching the experimental data extremely well. There is no experiment which contradicts quantum mechanics or disagrees with it. But that does not imply that the current formulation of quantum mechanics is exact. An exact formulation of quantum theory will not depend on classical time, right? Because suppose there are no macroscopic bodies in the universe, then there is no classical time. Yes, still I should be able to talk of quantum mechanics. Imagine that everything in the universe today is quantum, is in the form of electrons and atoms, and there are no planets and heavenly bodies, no stars. In principle, such a universe can be imagined even at today's low energy scales. So everything is quantum, so I should be able to have a formulation of quantum theory without having to use classical time. And such a formulation must exist at all energy scales, not just near the Big Bang. Today's universe is dominantly classical, but in principle it need not be so. And although it is said that quantum mechanics does not disagree with any experiment, I would say that that is only half the story. Quantum mechanics is not able to explain why fundamental constants take those values which they do. And my thesis is that that limitation is because we are working with the approximate quantum mechanics even at low energies. When we had this exact formulation of quantum theory, we will understand why fundamental constants take the values that they do. So that is the hypothesis. And so my goal is to build such a formulation of quantum theory in which classical spacetime does not occur at all. And let us start to go towards that goal. Right. So I'll help you visualize uh, where the exact formulation of quantum mechanics stands compared to the quantum mechanics that we have today. So I made this cartoon in which there are three layers: clouds, rain, and terrain, that is ground, what is called terra firma, earth with all its forests, trees, mountains, snow, us. So this is the terrain. So I'm using this analogy that there is a terrain, there is a in between, there is rain, and there is a cloud. And this picture of these three parts of the picture are of interest at all energy scales, even at low energy scales, at high energy scale. The cloud is an analog for the exact formulation of quantum mechanics. So what is happening in the terrain, as the quantum mechanics that we know today, there is a base, classical matter, the universe dominated by classical bodies is giving rise to classical space-time. So here you can put also stars and galaxies. This is our classical universe. It gives us classical space-time. In here we also have quantum systems like electrons. So if you want to write down the quantum equation for an electron, you will write the Schrodinger equation for the electron using the time that is coming from this terrain. We are looking for an exact formulation of quantum mechanics in which there is no classical matter. Remember, right? Suppose there is no classical space-time, no classical bodies, everything is quantum. How will I do quantum mechanics? That we call exact formulation of quantum mechanics. It turns out that over here, there is no distinction between space-time and matter. In a way, easy to understand. Space-time and matter are distinct only when matter is classical. Suppose everything is quantum, like in the cloud. So it's like an electron. The electron is everywhere and everything is quantum, so everything is everywhere. If everything is everywhere, then there is no space between things. So we think of space as space is that which is between bodies, time is that which is between events. In the cloud, in the exact formulation of quantum mechanics, everything is everywhere all the time. So there is no way to talk of space-time and matter separately. So the distinction between space-time and matter goes away. So I will not talk here of an electron in space-time. We talk of atoms of space-time matter. Okay? So in the exact formulation which is in the cloud, there is no distinction between space-time and matter. We have atoms of space-time matter. Now, when lots of these atoms, so electron also here would be called a particular kind of atom of space-time matter. A quark is another kind of atom of space-time matter. Here, when lots of atoms, such atoms entangle, a quantum to classical transition takes place. A classical universe arises because of spontaneous collapse or entanglement in the cloud. So that I call rain. As an analogy, what is rain? Rain is the process of transition from exact formulation where there is no space-time to a situation where there is classical matter and space-time. Once this transition happens, we have a terrain, and if you have an electron here, you could now describe it using the ordinary Schrodinger equation because you have acquired time. In the terrain, there was no classical time. It turns out that there is a new concept of time. So in the cloud there is no classical time, but it turns out that there is a new notion of time, which I will talk of in a moment. And so you can describe an electron either using the time from the terrain, or you can describe the electron using this exact formulation of quantum mechanics. And this is to be respected at all energy scales. Even in today's low energy universe, it looks like this, but I must still seek a cloud picture which is in the cloud, even at low energies, for reasons that I just described. Okay, so I hope you get some idea of what I am trying to do. Now our goal, mathematical goal, is to construct this exact formulation of quantum mechanics in the cloud. It turns out this is also a theory of quantum gravity. It is also a theory of unification of forces. So that is the significance of addressing quantum foundations. My claim is that we are stuck in theoretical physics, like why does string theory not work? Why does it predict so many different 10 to the power 500 vacua, as we saw in Professor Day's talk? It is because it is not addressing foundational questions in quantum theory, like the problem of time. When you address the problem of time, you are actually led to a theory of unification. And I want to, in the next few slides, give you my picture of the mathematics. There will be about 3 slides like this, which are slightly technical, because I want to give you a flavor as to how our group has worked to develop this exact formulation of quantum theory. So there are 5 mathematical ingredients which go into it. I'll give you some idea. The first is number systems known as division algebras. These are number systems in which division is allowed. Like, real number are a division algebra. Complex numbers are also a division algebra. So what is meant, if you have two numbers a and b in a division algebra, if you multiply them and if the answer is 0, then it is natural for us to say that either a is 0 or b is 0, or both are 0. Both cannot be non-zero. If a is like 3 times 4 will not give you 0. If you get multiply 3 with something and you get 0, then that something has to be 0. So in a division algebra, if a times b is 0, then at least one of them should be, a and b should be 0. Turns out there are number systems which are not division algebras. Namely, you take a non-zero, b non-zero, you multiply, the answer is 0. One such number system is known as the Sedenions. Sedenions are not a division algebra. Remarkably, there are only 4 types of division algebras: real numbers, complex numbers, this is we know. Then you may have heard of quaternions and octonions. Quaternions and octonions are very important in my work in this approach. When we want to get rid of space-time, when we want to get rid of classical time, we are going to replace every real number by a octonion. I'll explain what a octonion is. But the fact that in most of physics we have been using real numbers, in classical physics, complex numbers, in quantum mechanics, quaternions are actually basically 4 vectors. We use them in special relativity. We have never until recently used the octonions. They were discovered in around 1850, uh, soon after Hamilton discovered quaternions. A friend of his discovered octonions. But physicists until the last 20, 30 years, physicists did not find a use for octonions. But now, in the small community in which we work called algebraic unification, octonions have become extremely important and interesting. It seems they capture the mystery of particle physics. Why the fundamental constants take those values? It has to do with the octonions. And why the forces, why is there the strong force, weak force, gravity? Everything is related to this 8-dimensional number system. So we'll replace real numbers by octonions. Then we will have a new theory. Again, I'll tell you a few words about it in the next slide. A theory of dynamics called trace dynamics, which was developed by Stephen Adler and collaborators about 30 years ago. It is Newtonian dynamics with matrices. When you do Newtonian mechanics, positions are real numbers. But suppose positions were matrices, but you still write down Newton's laws of mechanics, but with using matrices. That is trace dynamics. We will use something known as non-commutative geometry, which generalizes the Riemannian geometry of general relativity. So what is non-commutative geometry is a situation where x times y is not y times x. Points do not commute. See, spacetime is made up of points which are described by real numbers. Those points commute with each other. In a so octonions do not commute with each other. A times b is minus b times a. They don't commute. Quaternions also do not commute. When you have replaced spacetime by entities which are described by such non-commuting numbers, you are in the domain of non-commutative geometry. This generalizes Riemannian geometry of general relativity and something known as the spectral action principle and the use of eigenvalues of the Dirac operator as a description of geometry. Let it pass if this is too technical. The fourth ingredient that goes into the development of this new formulation is something known as Clifford algebras for making spinor states from division algebras for describing elementary particles. Given the octonions, from octonions you can make Clifford algebras. From Clifford algebras you can make spinor states which describe elementary particles. So there is nothing there's nothing free about this process. It's a very rigid structure, so that's why we don't have the kind of infinitely many vacua that string theory has, because we have started from a foundational principle and work with octonions. Then the octonions dictate everything. There's no freedom left. And the symmetry is described by these so-called five exceptional Lie groups, which I'll say a little bit about it, labeled G2, F4, E6, E7, E8, and something known as the exceptional Jordan algebra. I'm sorry this slide is quite technical, but only one or two more like that, and then we'll talk nice physics. Let us understand this in a simple way. So when we use these ingredients, they help us go from the terrain to the cloud. What do I mean? We know the physics in the terrain. Forget quantum mechanics for a minute. Here everything is done by real numbers. I'm going to go from the terrain to the cloud by replacing real number spacetime by octonions, by replacing position vectors described by real numbers by matrices. So points, real number points become octonions, and real number valued position vectors become matrices. So we jump from here to here in a very nice and intuitive way. Just replace real numbers by octonions, and dynamical variables which are real numbers, replace them by matrices. It's a very intuitive way of doing things. So let me describe that intuitive process in a little more detail. In the terrain, this is physics, college physics. Suppose normally if you have free particles in space-time, it is described by a position vector qi, q0, q0, q1, q2, q3 in special relativity. These are the four components of the position vector q of the particle. So Q in boldface, it is the position vector, four-dimensional. These are its components, and in components you will write it like this. I hat, j hat, k hat are the usual spatial unit vectors, and t hat is a unit vector in the time direction. So given the position vector, you know that we have to write down equations of motion. This will be the equation of motion for a free particle. It is derived from this action. If you are familiar with the action principle, this is the half mv square is the Lagrangian, the velocity. Integrate the Lagrangian over time, you get the action. You vary the action, you get equations of motion. Plus, we have a symmetry. If you make Lorentz transformations on this vector q, it will give you another vector, but the equations of motion will not change. So invariance under Lorentz transformation is a symmetry, and mathematically the group that describes Lorentz transformation is this Lorentz group SO13. which generalizes the rotation group SO3. Okay, so this is the terrain, very simple standard Newtonian physics. Now let us go to the cloud. What will I do? Replace each space-time point by an octonion. There are reasons why we do this. It just gives us the unification theory. And you can ask why octonion. So I'd say because it works. Right now I'll leave it at that level. So what is an octonion? It is a complex number. Real number is just A0. Yeah, that's a real number. If you had A0 plus A1 E1, that is a complex number because where E1 square is -1. Normally we write iota. Iota and E1 will be the same thing. If you have A0 plus A1 E1, you have a complex number. If you had four of these, A0 plus A1 E1 plus A2 E2 plus A3 E3, that is a quaternion, where A3, A2, A1 and A0 are real numbers. If you have 8 of these, it turns out if you want to make a division algebra, you will only have A0, or you have one imaginary direction for complex number, or three imaginary directions for a quaternion, or seven imaginary directions and a real direction for an octonion. So 1, 2, 4, 8. These are the four division algebras. What is an octonion? Each of these EI square is -1. So there are seven imaginary directions in an octonion. It generalizes the complex number which has only one imaginary direction. And multiplication is non-commutative. EI times EJ is minus EJ times EI. So it's anti-commuting. This is a definition. And if you had an octonion, if you had a quaternion, you would have only three imaginaries. In octonion, there are eight imaginaries. So what are we doing physics-wise? So space-time in the terrain space-time was a collection of points. Each point is to be replaced by an octonion when you go from the terrain to the cloud. Okay. What else? You have to take this position vector which had four real number valued components like here, replace the position vector by a matrix vector. What does that mean? So instead of bold Q, I have written capital Q mu nu. Mu nu are matrix indices, mu rows and nu columns. You will make these components, instead of real numbers, you will make them matrices. So instead of four space-time directions, t hat, I hat, j hat, k hat, I have eight octonionic directions here written E1, E2 up to E7. 7 are non-commuting. Eighth is ordinary. So this matrix which describes the dynamics variables now. This matrix has eight matrix valued components. Here the components are real numbers. Here the components are real numbers. Here the components are matrices. So a matrix divided into other matrices, one matrix per direction, and eight of them. So this is a matrix valued vector. So instead of Q here, I will have capital Q. There are reasons why they have to be Q1 and Q2 separate. So this is my action principle in the cloud. There are only three fundamental constants: Planck length, Planck time, and h bar. That's it. Everything else now has to be derived. That's the goal. Instead of mass, I have written a unit 1 by length. That is doesn't matter. LP square by L square. This was like Q dot square. I have replaced it by Q1 dot dagger, Q2 dot. Dagger is what defines the adjoint. And now this is a matrix. I cannot have my action as a matrix. Action is a number, it's a scalar. So I take the trace of the matrix. So compare this. Instead of a free particle like this, I have a free particle like this. So this is how I would describe an electron in the cloud as opposed to the terrain. There's only one free parameter associated with the electron, which is this length parameter L. This entity is what I call an atom of space-time matter. There is no distinction between space-time and matter. And you should ask, oh, what is this time? Because you have given up time, you want a formulation without classical time. It turns out when we work with these non-commuting spaces like octonions, we are in the domain of non-commutative geometry, and for some profound reasons, non-commutative geometry gives rise to a new notion of time, which is you can call non-commutative time or Cohn's time after the person who found it. This is Cohn's time. So if I have lost classical time, but nature has very kindly given us another time, what Cohn's called God-given time parameter. So you are still able to describe evolution in the cloud. In the cloud, there is no classical space-time, but there is a time parameter which allows you to describe evolution. The universe is made up in the cloud as a collection, enormous collection of STM, space-time matter atoms. The STM stands for space-time matter. So there will be a one action for every cloud, every atom of STM atom. How many STM atoms are there in the universe? I don't know. At least 10 to the power 80, maybe infinite. We just need them to be a very large number. So the cloud has a mathematical description. Notice that there is no distinction between space-time and matter yet. As I said, I must propose a symmetry principle, symmetry group. Here it was the Lorentz group, Lorentz symmetry. It turns out that if we work with this group called E8 cross E8, it gives us a theory of unification of all the forces. So you get some idea, I hope, as to how I construct the cloud given the terrain by going from real numbers to octonions and from real numbered variables, dynamical variables Q to matrix valued variables. So because we work with the trace of matrices, this is called trace dynamics. So you can vary the action and get equations of motion. So this is like doing Newton's work, doing Newton's mechanics, but with matrices and on octonions instead of ordinary spacetime. That is what trace dynamics is. It turns out this is a theory of unification of forces. How do we understand that? So we are now in the cloud. We are here. We have constructed an exact formulation of quantum mechanics here. We must explain how we recover the terrain from here. Because terrain is what we observe. This we don't observe. We haven't yet seen this in the lab. From here can we come to ordinary world that we see? So this is string theory also starts from something like a cloud. Then they do compactification of 6 out of the 10 dimensions, and they try to reproduce the terrain, but they land up with 10 to the power 500 possibilities, and it is not clear whether our universe is even contained in that. Like Professor Linde said, we have not yet found it. So what we have done, we have a theory in the cloud, and we have a proposal for coming to the terrain which reproduces the observed universe. No compactification. We are not in 10 dimensions. We are in 8 octonionic dimensions. String theory has 10 space-time dimensions, 9 space, 1 time. No, we have 8 octonionic dimensions plus Cohn's time, which describes evolution. And from there, without compactification, we recover the terrain. So what happens? So in the cloud, what we have is what I call the pre-space-time, pre-quantum universe, which undergoes an expansion, some kind of an inflationary expansion, until the electroweak scale. So the cloud, presumably the universe began as a cloud at the Big Bang scale, underwent some expansion. That part is we are still developing. Up to the electroweak energy scale of 1 TeV, when a symmetry breaking takes place in the following manner, we have E8 cross E8 groups. Both the E8 groups undergo a branching and symmetry breaking. I am short of time. Just to say in brief that when you do this kind of a symmetry breaking, what emerges is the classical space-time of the terrain. At the electroweak scale, because of such a symmetry breaking, we get classical spacetime in the terrain along with the four known forces: strong force, weak force, electromagnetism, gravitation, and one new predicted force which we have called dark electromagnetism. So when symmetry breaking happens, the octonions are replaced by real numbers. That's the quantum to classical transition. That is how space-time is recovered without doing any compactification. So octonion has 8 directions. 4 of them become space-time directions. The other 4 become internal symmetry directions in which the strong force, the weak force, and the electromagnetic force live. And we didn't have to do anything by hand. How to get 4? It comes out naturally that way. There's a reason why space-time emerges as 4-dimensional. Then those STM atoms which do not take part in the quantum to classical transition, they stay quantum in nature. They stay in the cloud, but I can also describe them using the terrain. So now the technical part is over. So we have a formulation of quantum theory without classical time. We have a unification theory, E8 cross E8 unification. What do we learn from it? If you work in the cloud, you have much more information than in the terrain. The cloud is a more precise description even at low energies. An example is a macroscopic solid. If you take a stone, you just know its surface. You don't know that there are atoms inside. But today physicists know that the properties of the stone are determined by the atoms inside. So atoms and the macroscopic solid. The terrain analogy is the macroscopic solid. And the cloud are like the atoms. That's why I call them atoms of space-time. So I took this screenshot of Professor Linde's slide the other day because I liked it very much. So I'm reproducing it. Let's read it again. I would like to state a theorem, Einstein says, which at present cannot be based upon anything more than a faith in the simplicity, intelligibility of nature. There are no arbitrary constants, that is to say, nature is so constituted that it is possible logically to lay down such strongly determined laws that within these laws only rationally completely determined constants occur. My claim is that we have arrived at that stage. From Einstein said this in 1949, and although Professor Linde said that this dream is not fulfilled because of the multiverse, I am claiming that this dream is being fulfilled because we work with the octonions. The octonion structure is so rigid that if we make space-time with octonions, space-time tells matter what to be. So we say in gravitation, matter curves space-time, space-time tells matter how to move. Now space-time not only tells matter how to move, it also tells matter what to be. That is why are there electrons, neutrinos, and quarks? Why only those particles? Why 3 fermion generations? Why do they have those particular values for masses? We are now able to start being able to answer these questions. And I give you one example, which we are quite happy about in our work. And that is the masses of elementary particles leaving out neutrinos. These masses take very strange values. Have a look here. Electron, up quark, down quark, strange quark. Look at these numbers. They don't show any obvious pattern. And I can make it easier for you to visualize. These are the elementary particles: quarks, electron family, down quark family, up quark family, and the neutrino family. There are 4 families and there are 3 generations. And then what are the charge ratios? Neutrino is uncharged, electrically uncharged. The down quark charge is 1/3 that of the electron. The up quark charge is 2/3 that of the electron. Within a family, all the three particles have the same electric charge. The electron, muon and tau lepton have the same charge. Similarly, downstream and bottom have same charge, etc. But look at the masses, how the mass changes. 4, these are mass ratios. If the electron is 1, the top quark is 3,40,000, 8,180 for bottom quark, 207 for the muon. Where are these numbers coming from? We discovered in our work in the cloud with the octonions that we can actually prove from first principles that the observed masses are actually nothing but these following ratios which are derived from theory. Suppose I set the down quark to 1, then the electron is 1/3, the up quark is 2/3. Strange quark is this number. Notice this very pretty square root 3 by 8 which comes everywhere. And then other than that it is 1, 1/3, 2/3. And I can write, you can see this paper, and I can write this in a simpler way in this table. If you define delta as this number square root 3 by 8, these 3, 4, 5, 6, 7, 8 numbers define all the funny numbers that you see. And we work with square root. So square root mass ratios, up quark with respect to the electron is 2, down quark with electron is 3. Similarly, like tau lepton to the muon, these are theoretically derived fractions where delta is square root 3 by 8. You put in the value of delta, this is the number in decimals. Like I take this number, delta root 3 by 8, decimal value is this. And this is the experimental value. So we agree to within few percent or few tens of percents. Here there is a bigger disagreement. 3, 2.34, 2, 1.59, 4.15, 4.46, 6.7 here, 4.15, 4.11, 14.09, 14.23. So there is not perfect agreement, but the so-called mass hierarchy is observed, reproduced. Like, the top quark was 3,40,000 times the electron. That is explained by these ratios, which, as I said, are derived from theory. Okay, now to the last part of the talk. I'll finish in 5 minutes. What are the possible implications for cosmology? Before the electroweak symmetry breaking, the universe is a collection of enormously many atoms of space-time matter. There is no distinction between matter and space-time. No distinction between the physical. Yes, I forgot to emphasize this. There is not only is it that matter and space-time are indistinguishable, I cannot distinguish the physical world from its description by mathematics. What is the definition of an atom of space-time matter? It is defined by this action. That's all I can say. I cannot say hold a STM atom in my hand because there is no space-time. So what is meant by holding? This is it. This is the fundamental entity of physical universe from which everything is made, and it is described by this mathematics. So I say that at the most fundamental level, there is no distinction between the physical world and the mathematics it describes it. So where does mathematics live? I don't know, but perhaps mathematics is equal to physics, and that is the cloud. Why is the cloud there? I don't know. But at least you can say, why is the universe there? I think because there is mathematics. Why is there mathematics? I don't know. So now, was the Big Bang a spontaneous collapse in a sea of STM atoms? So so this is the fundamental state of the universe. It's a collection of mathematical collection of STM atoms, which I have shown with like these balls, but of course they are not localized. There is no space-time here. Maybe some dynamics is happening in these STM atoms, some entanglement, some spontaneous fluctuation where lots of STM atoms come together and collapse to form what we call a universe. Let me make it a little better. Imagine, this is the analogy. Imagine gas molecules in a box undergoing a rare fluctuation. So these are like my STM atoms. They have been going around, the gas molecules are going around in the box. Every once in a rare while, extremely rare, there will be fluctuations such that the whole gas will come in one corner of the box. What will happen after that? Then it will start spreading out. So my claim is that perhaps, I don't know how to prove it, that from these STM atoms, if there is a spontaneous localization, after that what happens is the Big Bang and the expansion. So this is our universe is created after, as the opposite of spontaneous localization. So I actually I asked, I in the last few months I'm interacting very heavily with AI like ChatGPT Pro and Anthropic's Claude. They are really becoming very useful and important for research. So I asked this question to Claude. Given all molecules in one corner of the box, maybe because there was a large spontaneous fluctuation, so spontaneous fluctuations send the molecules to a corner of the box. What will happen next? Will it be like the Big Bang, an explosion, expansion into the whole box, proceeding towards homogeneity? Okay, so this is the answer. See how well is AI thinking these days. What a beautiful analogy. Yes, exactly. A large language model is saying things like this. This is the answer from Claude. A spontaneous fluctuation concentrates everything into a corner, and then the system expands outward towards equilibrium, just like the universe after the Big Bang expanding towards homogeneity. So in detail, yes, this is exactly like the Big Bang in miniature. The molecule, this is again Claude saying. The analogy to cosmology is striking. In your octonionic theory, the universe begins in a collection of enormously many STM atoms in a unified E8 cross E8 phase. The analog of all the molecules packed in one corner. Inflationary expansion then drives these atoms outwards, and when critical entanglement triggers spontaneous localization at the electroweak scale, classical spacetime crystallizes out. The analog of the gas reaching thermal equilibrium and filling the box uniformly. The sequence of our four pictures tells exactly this story: uniform equilibrium, corner localization, expansion, and approach to new equilibrium, etc. So, maybe there are multiverses in the following sense. Underlying its substrate is a mathematical collection of STM atoms. Spontaneous localization is happening all over. In infinite, I don't know. What even infinite means, there's no space time here. So universes are perhaps being born all the time. All the time means Cohn's time, the non-commutative geometry time. And within the universe, then electroweak symmetry breaking happens. It forms stars and galaxies. Those stars and galaxies will eventually all become black holes. Black holes will evaporate by Hawking radiation, which is quantum. Once everything is quantum, you are back to STM atoms. So maybe like in the Indian philosophy sense, universes are being born and dying all the time. Here is our universe, we are here. Once it, for long in the future, after hundreds of billions of years, it will again evaporate into Hawking radiation via black hole. It will go back to this state. It will go back to the STM atom state. And then again, the difference from Professor Linde's case is this is like a multiverse, but the laws of physics are the same everywhere. The fine structured constant is always 1 by 137. There are always only four fundamental forces. This is where I differ from him and from string theory. I agree with Einstein. The universe is rigidly determined to be what it is, except that we may have multiverses. So nothing wrong with multiverses, but laws of physics are universal. And this is my last slide, summary and outlook. There must exist at all energies a reformulation of quantum theory which does not depend on classical time. We have developed such a reformulation by using the laws of trace dynamics, non-commutative geometry, and replacing points by octonions. This is a pre-spacetime, pre-quantum theory. The fundamental entities of structure are atoms of space-time matter. They obey a simple action principle based on matrices. The assumed symmetry group is E8 cross E8. We have a candidate theory of unification, which is an alternative to string theory. I invite you to ask ChatGPT to compare my E8 cross E8 octonion theory with string theory and say which is better in which way. I tested that. So it's a very long 10-page answer that ChatGPT Pro gave, saying in what way my work is less developed than string theory and in what way it is more developed. Our biggest strength is we have predictability, falsifiability. We predict things that can be tested by experiment, and we don't have 10 to the power 500 vacuum. We have only one vacuum, that is the observed universe that we see. Symmetry breaking at the electroweak scale gives rise to the observed spacetime and observed fundamental universe forces. We are able to derive values of some of the fundamental constants like mass ratios. This is ongoing work. The ambition is that every fundamental constant will follow from the octonionic picture. More work remains to be done to understand how we go from the cloud to the terrain, why neutrino masses arise, what is dark matter, and lab tests of the predictions that we have made. I'll stop here. Sorry for overshooting my time. Thank you for your attention.
Thank you, sir. Thank you. Thank you very much. Yeah, without further wasting much time, maybe we can take questions. This is from Bak from Bangalore University, India. He is asking, sir, please explain how symmetry breaking occurs from the cloud to terrain.
Yeah, very good question. I did not go into some enough details. The symmetry breaking is actually a transition from quantum to classical. So it is like the Higgs mechanism, but for a reason, I have to make one assumption that the universe has 10 to the power 80 STM atoms, observed universe. If I make that one assumption, if I take that one number from observed universe, 10 to the 80, then I can argue that when the universe cools down to a TeV scale, a quantum to classical transition takes place precisely around the TeV. This I can derive if I take n as 10 to the 80. And that is where the symmetry breaking happens. So the symmetry breaking is a quantum to classical transition. That is the best way to look at it. And then the branching that I showed, SU3 cross SU3 cross SU3 cross SU3, is one possible branching which I can argue is favored for on certain mathematical grounds. I don't know if I answered your question. The symmetry breaking is a quantum to classical transition which takes us from the cloud to the terrain, and it is essentially the Higgs mechanism of particle physics. But there is a second Higgs, there are two Higgs bosons involved. So we predict that there is one new Higgs boson which should be looked for in the laboratory. If it is not clear, please email me. I try to answer your question better.
Uh, Wonderful, sir. Thank you. Maybe it will help him. Yeah, can we have next question quickly, please? Yes, this is from Harishankar Nath Tiwari from University of Petroleum and Energy Studies, Dehradun, India. Sir, if space, time, and matter emerge from the cloud level, is it theoretically possible to engineer correlations at that level that effectively bypass classical distance?
Thank you. Very nice question. Very nice question. You are absolutely right. In the cloud, indeed, there is no classical distance. There is no notion of space-time and classical distance. You are absolutely right. And there are, so you can call quantum correlations, as you said, but there is no distance. True.
Yes. Thank you, sir. Thank you. Next question is from Jagdishwar.
Yes.
Why the time 10 power minus 12 seconds is always mentioned?
Hmm.
How we get the value? Can you please elaborate?
Yeah, thank you. Very nice question. So we have made one assumption that the universe began at the Big Bang, not infinite energy, but Planck energy, 10 to the power 19 GeV at Planck time, just 10 to the minus 43 seconds. So this is the starting assumption, 10 to the 19 GeV at 10 to the minus 43 seconds. Then as the universe expands, it cools. The energy, the average energy comes down. And there is a scaling law, which I have assumed, I must say, I must confess, your question is good. In cosmology, there is a standard scaling law, which I assume, that the average energy falls as square root of time. Yeah? E goes as t to the half, square root t. So energy has to come down from 10 to the 19 GeV to TeV, which is 10 to the 3 GeV. Energy has to come down by 16 orders of magnitude, which means time has to come down by 32 order of magnitude because E is going as square root t. So 10 to the minus 43 and 32 orders of magnitude, that is 10 to the minus 11. So minus 11 minus 12 roughly. So I hope you get the picture. There's an energy time relation. E goes as square root t. As the universe cools, I come down from Planck energy to TeV. I know how much time I will have passed by in that much. I hope you get the idea. Again, otherwise, please write to me.
Yes, sir. Can we have one last question? Yes, sir. This question is from Pradeep Kumar, Kendriya Vidyalaya, Sangathan, India. Thank you for your insightful explanation, sir. I would like to humbly ask, quantum mechanics explains the behavior of particles at the atomic and molecular level very well. And the small components seem to continuously build up into large structures like planets and galaxies. However, quantum theory does not fully explain large scale phenomena, while great general relativity does not describe quantum behavior at very small scales. What kind of theory or understanding can bridge the gap between quantum mechanics and general relativity? I hope this is first part of the question, and one more follow-up question is there. It is like, so would you like to answer this question first,
Yeah,
sir?
yeah,
Or
let us do this first. Good. So the theory that I have developed is doing answering precisely your question, which is the theory which bridges the gap between quantum mechanics and general relativity. It is this exact formulation of quantum mechanics in the cloud. So in the cloud, we have atoms of space-time matter, we have octonionic space, we have trace dynamics for matrix valued degrees of freedom. We know how these atoms of space-time evolve. So what the cloud theory is the gap, it does bridge the gap between quantum mechanics and general relativity. So that's precisely what we are doing. Also, second question, how should we understand the collapse of the wave function? What really happens during this process? Is it possible that our current theoretical framework is incomplete, or could hidden variables be involved? Yeah, very good. So trace dynamics, the octonionic theory in the cloud, actually also explains collapse of the wave function. As you rightly pointed out, quantum mechanics has the quantum measurement problem. It cannot explain collapse of the wave function because the Schrodinger equation is nonlinear. The collapse process, Schrodinger equation is linear. The collapse process is nonlinear. It breaks linear superposition. So we need to modify quantum mechanics in order to explain collapse, and the octonionic theory in the cloud turns out to be the right kind of modification which explains collapse. What happens really? This is related to also what are known as objective collapse models or the Girardi-Rimini-Weber theory of collapse. The Schrodinger equation gets modified to have an imaginary part in the Hamiltonian. That imaginary part is also nonlinear. A nonlinear imaginary correction with the Schrodinger equation, which we don't put by hand, it comes out of the theory. A nonlinear imaginary part in the Hamiltonian breaks superposition. So the breaking of superposition is very negligible for small systems like electrons, but it becomes very significant for large objects like tables, chairs, and planets. So collapse happens very rapidly for large objects in this theory. So I should say that this Girardi-Rimini-Weber theory of collapse is not yet confirmed in the lab. Every experiment still agrees with quantum mechanics. To explain collapse of the wave function, we need to modify quantum mechanics, but such modifications are, as of now, only in theory. They have not been detected in the lab, though people are looking for these modifications. So, in real truth is that the collapse of the wave function continues to be an unsolved problem. The octonionic theory that I described is one way to solve the collapse problem. Again, this is there in my papers, which you can find on my TIFR website, or please write to me if you want more details and references. Thank you.
Thank you, sir. So we encourage all the participants to write to sir if you have any further questions. And maybe our technical team can also forward the questions that we received. Sir, thank you actually for bringing up new concept which is giving hope for our understanding. So maybe it will help us, mostly the physicists, to explore and come up with a unified theory as you are proposing. Maybe I hope it will one day give us or at least bridge the gap to some extent. So thank you for your wonderful insight and thank you for joining us. So on behalf of Bhaktivedanta Institute and all the audience that are present here, we would like to sincerely thank you for your new proposal of this new concept. And this, I think our audience has gained very much. Maybe few questions may come to you, I think.
Yeah, sure. I'll be happy to interact with the participants. They can write to me. Thank you very much for listening. I enjoyed talking to you.
Thank you, sir. Thank you. Thank you. We hope to see you more frequently so that we can learn more from you.